All right, for problem three, you have a velocity versus time graph. You have a motorcycle and a car. At time t0, the car and motorcycle at the same location. And we're supposed to explain sort of the motion, discussing position, velocity, and acceleration throughout this whole thing. So what I'm going to do is I'm going to just kind of type out a response here as clearly as I can. So we know that initially the car will be moving. Initially, the car will be moving with a greater velocity than the motorcycle. It will move ahead in position initially, but the motorcycle will steadily increase in velocity until at time 30 seconds, the two vehicles have the same velocity. At this point, it will be the motorcycle that is moving with a greater velocity while still accelerating. At some point in the future, the motorcycle will overtake the car. So I've mentioned position, I've mentioned velocity, I've mentioned acceleration. It's kind of a lot here that actually does happen in the situation. Even if this isn't exactly everything, it is, still describing the things that are required. You can get a lot more detailed, you can talk about the area under the curve, but it does bring that up in the next part. So I don't want to talk about it in this section yet. I should also mention that I guess at this point we know that the car, the greater velocity, greater constant velocity in the motorcycle. So I'm not sure I mentioned, but the car's velocity is constant. You can include values and all that as well. Okay. So moving on from there, and part B, it asks us to determine which time the car and the motorcycle are in the same spot. Justify your answer. Really, it's really simple. I'm gonna look at the area. Okay. For the area, if I look at the whole thing for the car, right, that's going to be a rectangle, and that rectangle has a base of 60 and a height of 20. Okay, so the area of that section there is going to be 1200 meters, and so that's my displacement from the initial position. So it would be 1200 meters ahead of where it started. And I can do the same thing for the motorcycle. Remember, we're just figuring out what the area is for these two values, for these two vehicles under the graph, right? So we looked at the graph of the triangle, which is from there to there. The area of that section there would be 60 times 40 by 1/2. So 1/2, 60 times 40. That's the area of the triangle, right? It's base times height times 1/2. That'd also be 1200 meters. So at 60 seconds, it's also traveled 1200 meters. And so that's when they would actually have the same position, right? I kind of knew that intuitively just because I know that, you can see this triangle. Its whole area is basically half of the graph, right? From corner to corner diagonally. You can tell the same is true for the rectangle. It's also half the whole area of the graph, but you can kind of, figure it out. It's trial and error as you try to figure out where the two areas have the equal value. But usually, there's some sort of inclination where they should be equal to each other. Okay. So, yeah, so for justification here, you would just say you calculated the area under each graph to determine displacement. Which is 1,200 meters at 60 seconds. So derive expressions for the positions, the car, and the motorcycle as functions of time. Really just kind of looking at the graphs and writing equations for those graphs in terms of position rather than the velocity that you're seeing there, right? So I know this velocity here is 20 meters per second, and then that the motorcycle is climbing up, right? So it hit a velocity of 40 up here after 60 seconds. Okay. So my expression for the position of the car would be that it starts at 0 position and its initial velocity is 20 meters per second, and then time, right? Then there's no acceleration, so that would be a term that also kind of ignores. So it's just 20 meters per second times time is my expression for the car. And then for the motorcycle, I would say, well, I know that it's accelerating, but I also know that it started at 0 position. Its initial velocity was 0, so it started from 0 velocity. And then its acceleration would be the slope of that graph that we have there, the velocity graph that we have, right? So 40 is my rise, 60 is my run. So this would be 2/3. So 40 over 60, right, would be 2/3. So 0.67 meters per second squared times t squared. All right, so this expression would just be 1/2 times, so 0.67 meters per second squared over 2 times the time squared. Those are our two expressions here for the displacement or position as functions of time.